Having considered the mechanism for ester hydrolysis under basic conditions, we now look at the mechanism for ester hydrolysis under acidic conditions. Okay, so the net reaction is that we're starting with an ester, reacting it with H3O+, which implies that you have H2O present in solution as the solvent, which will be necessary in the mechanism. And the product then is a molecule of carboxylic acid plus a molecule of alcohol. So in this reaction under acidic conditions, the carboxylic acid is the direct product of the reaction. It does not have to be formed by addition of acid after the basic mechanism is over. Okay, so when we look at this mechanism, it is almost exactly the same as the mechanism for transesterification under acidic conditions, except that in this case, instead of another ester coming in as the nucleophile, water is going to come in as the nucleophile. So let me walk you through this. Just like with transesterification, we have a proton transfer to start the mechanism, proton transfers in the middle of the mechanism, and a proton transfer at the end of the mechanism that are bookending the nucleophilic attack followed by the elimination. So the first proton transfer is that we use H3O+ to protonate the ester on the carbonyl oxygen. We've got to protonate it on the carbonyl oxygen because it is the carbonyl carbon that will get attacked by the nucleophile, and protonating on the carbonyl oxygen makes it more susceptible to nucleophilic attack. Okay, so we protonate it on the carbonyl oxygen. That requires, of course, 2 hours for the proton transfer. And then in the second step, the water comes in as a nucleophile to attack the carbonyl group. Once again, we break the CO pi bond, put those electrons onto the oxygen, and then this leaves us with a neutral OH group bound to what was the carbonyl carbon. The OH, the water that came in, that oxygen still has both of its hydrogens on it and still has a positive charge. So at this point now, we need to think about where we're going. We've got to get rid of a molecule of methanol, which means that the OCH3 down on the bottom of this structure is what's going to have to leave as a leaving group. Except because we're under acidic conditions, it cannot leave as OCH3-, it has to leave as neutral CH3OH. And in order to leave as neutral CH3OH, it needs to pick up a proton. So we have to shift a proton from the oxygen that came in as water to the oxygen that's going to leave as methanol. We can do this in one step via an intramolecular proton transfer, which is specifically what I drew for the transesterification mechanism. Here I'm showing the mechanism in 2 steps, which is an alternative way of drawing it. I just want you to see both of these possibilities, but recognize that each one of them is a possibility. So in this case, we're going to take a molecule of solvent, namely water, and have it remove the proton from the OH2+ that has just come in. This now makes a neutral intermediate shown on the right-hand side here. And then in a second proton transfer, we're going to use the H3O+ that we just generated and donate that proton to the OCH3, so that we now have CH3OH+ bound to the central carbon. Okay, again, these are both proton transfers. They both require 2 hours, as you have seen many times before. Now that we have made the possibility for methanol to leave as a leaving group, we're going to have it leave. And just like we did in the transesterification mechanism, we're going to have the reformation of the carbonyl group and the expulsion of the leaving group happen in the same step. Okay, so we're going to use electrons from a lone pair on the OH oxygen, have them come down and reform the carbonyl group, and then at the same time, so as not to have too many bonds to carbon, we're going to kick off methanol as a leading group. This leaves us now with a protonated carboxylic acid. That may seem a little silly to you because isn't a carboxylic acid already an acid? But it is acidic at the OH, of course. You can actually have a carboxylic acid that's also protonated on the carbonyl oxygen, which is what you have here. This is, of course, also the alternate resonance structure for a doubly oxocarbocation. So, but the protonated carboxylic acid resonance structure, in addition to being the major one, is the one that we need to get to the product. So all we have to do now is use a molecule of water, deprotonate the protonated carboxylic acid, and that will leave us with the neutral carboxylic acid that we want as the final product. It will also regenerate the H3O plus that you need to start the mechanism all over again with another molecule. So the only note that I wanted to add to this, as I said as I was going along, is that instead of 2 intermolecular proton transfers to and from the solvent, you could have written this in 5 steps using an intramolecular proton transfer from the oxygen with 2 hydrogens to the OCH3. Okay, so that's hydrolysis of esters under acidic conditions. It turns out if you look at this mechanism that all of these reactions are reversible, and this reaction actually can be carried out in the other direction, forming an ester from a carboxylic acid and an alcohol. That is called a Fischer esterification, and we're going to look at that in detail in the next video.